grade 10s. So in this video we are going to look at the kinetic molecular theory, especially the heating curve. So I have a question in front of me, which is question 3 on paper 2. So this question is dealing with the heating curve. So let's read the question and then we'll look at the following questions. So the statement says the heating curve for a pure substance at atmospheric pressure is shown below. So this is the heating curve of a pure substance, or for a pure substance at an atmospheric pressure. So these are the questions. Question 3.1 says write down the following for the pure substance. They want us to write the melting point of that substance and the boiling point of this substance. The melting point and the boiling point. Now, before we go to the graph and answer this question, let me quickly explain the heating curve with the boiling points and the melting point. Okay, now in this example, we have a heating curve of water. Now the graph looks like this. So you have this straight line curve. Now at this curve you can see that the temperature is between negative 10 Celsius degrees and 0 Celsius degrees. That means at this state, at this phase, the water is in the solid form because the temperature is below 0 Celsius degrees. And then when the temperature reaches 0, we call this point now the melting point. We call it the melting point. Now the water is melting at this state. I'm going to say MP, melting point. So all of this part is the melting point. And then as the temperature increases now from 0 to 100, this state or this phase of water, we said it is a liquid phase or liquid state. So I'm going to say solid state, I'm going to say liquid state, up until the temperature reaches now this point. Now at this point, that point is 100 Celsius degrees. We call this point now the boiling point because the water is boiling at that state. I'm going to say this is MB. Oh, sorry, what am I doing? It is boiling point. It is BP, boiling point, melting point. So as the temperature increases now, the state of water now after 100 Celsius degrees will be a gas state. So we have 2 points on the curve. We have this point, which we call the melting point. So that point we call the melting point. The melting point of water is 0 Celsius degrees. Then we have the second point, which we call the boiling point. The boiling point of water is 100 Celsius degrees. So we have 3 states of water. A water in a solid state that is below 0 Celsius degrees. We have a liquid state that is between 0 and 100 Celsius degrees. Then above 100 we have a gas state. This is a gas state of water. So we call this curve now the heating curve of water. Now why water is considered a pure substance? The reason water is considered to be a pure substance is because the melting point is 0 Celsius degrees and the boiling point is 100 Celsius degrees. So water is a pure substance because of that. So we must take note now of the melting point and the boiling point. Now let's define what is a melting point and what is a boiling point. So if you look at your substance at this point was a solid. Now that means that the particles, let's say we had a ice block. So the particles of water inside the ice block, they were like closely packed to each other. There was no space to breathe. All of the particles, they were closely packed to each other. There was no space to move. So we increased the temperature now from negative 10 Celsius degrees to 0. Now, when the temperature now is at this point at 0 Celsius degrees, now the ice, let's say this was an ice, starts now to melt. To melt, it means that the solid state now is becoming a liquid state. So melting means when a substance changes from solid to liquid state. That's melting. But the melting point, the point where the water starts to melt, this point we said melting point is a temperature where the substance given enough heat becomes a liquid, where a solid substance becomes a liquid substance. So at this point at 0 Celsius degrees, when you apply enough temperature on this ice, now this ice will become a liquid. So the temperature at which now this ice becomes liquid we call a melting point. That is the temperature. Now as you increase the temperature further, remember now we have a liquid now. So this is a liquid. When water now is liquid, now there is space between the molecules of water or particles of water. There is space now, and these particles begin to have room to move. So they have room to move. So these are the gas molecules, these are the water molecules in a liquid state. We apply more temperature to this liquid. The water will reach a point now which we call a boiling point. A boiling point is a temperature now where the liquid state of a substance become a gas. So this point we call a boiling point. So that means that boiling now is when the liquid becomes a gas. And what temperature is that? That is 100 Celsius degrees for water. So we have now a gas phase of water. Now this is a gaseous phase of water. There is more space for the particles. The particles have enough space to move around. Now when you look now at the temperature, now the temperature by definition we said it is the measure of the average kinetic energy. Now the temperature is the measure of the average kinetic energy, and we know that the kinetic energy has a formula that says half mv squared. That means that when the water was still ice, the average kinetic energy was very low because the movement or the speed or the velocity of the molecules was very, very little. There was no space to move. But as we increase the temperature, we are also increasing the average kinetic energy, which means we are increasing now the velocity of the particles. So when ice has turned into liquid, that means that now the average kinetic energy of the molecules has increased. In other words, these molecules now, they have a higher speed or motion than in the previous state. As we increased the temperature further, we discovered that the kinetic average temperature was also increased. The kinetic average energy was also increased. Now at the gas state, the velocity of the molecules is higher than that of the liquid. So by increasing the temperature, we are actually increasing the average kinetic energy, which means that we are increasing the speed of the molecules. So there's a higher collision of gas particles in the gaseous phase than in the liquid phase than in the ice or solid phase. So this is simple examples of a heating curve. So let's go back now to our question and check what they were asking us. So the question was saying write down the write down the following for the pure substance: the melting point and the boiling point. So they want us to look for the melting point and the boiling point of this substance. So according to our knowledge now, we know that the melting point of this substance is this first horizontal line. Now this first horizontal line, I'm going to use a color red, if you can see. So this first horizontal line, we know it is the melting point. Now the second horizontal line, we know this one is the boiling point. So I'm going to say that one, boiling point. So always you must look for the horizontal line. The first one will be the melting point. The second one will be the boiling point. So it's not always going to be at zero, because of that means this substance now is not water. But our example for water, we know that the first horizontal line is at zero because of this is water, and the boiling point is at 100. So when the first line is at 0 and the second line is at 100, then you must know that you are dealing with water. But now when the first horizontal line is looking at a different temperature and the boiling point is looking at a different temperature, that means this is not a water molecule. So they want us to tell now what is the melting point and the boiling point. So we need to look now for the melting point. The melting point is this temperature, but we don't know what that value is, so we need to find that value. And the boiling point now is this temperature. If you can see the red line is going straight to the y-axis. The boiling point is that temperature which is above 90 Celsius degrees. So let's first now look at this one, which is the melting point. Let's find out what is that value, because they didn't tell us. And then we'll look now for the boiling point after this one. So this is your graph now. So we are looking for the melting point. We know the melting point is this temperature right here. So we want to know what is this value that this arrow is looking at. So this graph now, we need to check how many blocks between 30 and 60. How many blocks between 30 and 60? Let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 blocks between 60 and 30. So the difference between 60 and 30 and 90 and 120, you can see that this graph is a graph of 30. So we have 30, 0 plus 30 is 30, plus 30 that's 60, plus 30 that's 90, plus 30 that's 120. So the difference here is 30. And we know that there are 10 blocks between 30 and 60. So each block now must be must have a value of 30 divided by 10, that is 3. That means that you add 3 10 times, then you're going to find 60. Let's check that. We add 3 times 10, that's 30. So that means that this is 30 plus 3, that is 33. Remember, we are looking at this point. We're going to count now up until we get at this point. So how many blocks is that? 1, 2, 3, 4, 5, 6, 7, 8. So we're going to add now on 30. We're going to add 8 blocks, which has a value of 3. So that means that we have 30 plus 8 times 3, that is 8, 16, 24. So we're going to add now 24. 30 plus 24, that should give us 54. So that means this value now must be 54. Because we added 8 blocks which has a value of 3 each. It's like 3, 6, 9, 12, 15, 18, 21, 24. So we added 24 on 30, we're going to come to 54. So going now to our question, we know now the melting point is 54 Celsius degrees. Now let's look now for the boiling point. The boiling point now is this point. From there, going further to the left on your y-axis, this is the boiling point. Remember, each value is 3. So from 90, just add 3. So that means that value is 93. So that means the boiling point is 93 Celsius degrees. Yeah, so these are the melting points and the boiling point. 3.2, is this pure substance water? Give a reason for your answer. We already stated that a water molecule must have a boiling point, a melting point of 0, and a boiling point of 100. So only these are the melting point of water and the boiling point of water. But this substance now, its melting point is 54. Its boiling point is 93. So this is not a water molecule. When they say give a reason for your answer, you just tell them that because the melting point is not 0 Celsius degrees and the boiling point is not 100 Celsius degrees. That's the reason we say it's not water. What is the physical state of the substance at point X shown on the graph? The state of the substance at point X. Here is point X. Point X seems to be below the boiling point. Remember, the state of the substance here is a solid. The state here is a liquid. The state here is a gas. So at this point now, we know the state is a liquid. Look again. This is the point X, that dot. So that dot seems to be below the boiling point. That means the state is the liquid. So we know the state at point X is liquid state. And then look at following question 3.3.2. What is the physical state of the substance at room temperature? Now, what is room temperature? Room temperature, by explanation, room temperature is a temperature like between 20 Celsius degrees to 25 Celsius degrees. This is the room temperature. So where is 20 Celsius degrees and to 25 Celsius degrees. It must be below here. It's like somewhere here. So all in this region, we know that the substance is a solid because room temperature is below, is below 30. It's like from 20 to 25. This region here is a room temperature. So this substance at this region is still a solid because of it started to melt now at 54. So every temperature, all the temperature between 54, we know that is a solid state. So that means that at room temperature, this substance is a solid. It only becomes a liquid after 54 Celsius degrees. Last question, what happens to the temperature while the substance melts? Explain this observation. Okay, let's look at this one. So what happens to the temperature? What happens to the temperature while the substance melts? Now, the substance is melting at this point. The substance is melting at this point, at the melting point, at this point. So at that point, what is happening now to the temperature? Remember, on the y-axis, on the x-axis, we have time. So they didn't tell us the time. Let me just put some time here. Let's say that every 5 minutes, so starting from 0 to 5 minutes, the temperature was increasing. As you can see, the temperature was increasing. Now, when the time is 5 minutes, that's when now the substance starts to melt. From 5 minutes now to 10 minutes, all this time the temperature is constant. The temperature is still 54 Celsius degrees. For the next 5 minutes, the temperature is 54 Celsius degrees up until here. Let's say that is 12, up until 12 minutes. So, and then at 12 minutes up to 15 minutes, the temperature now is increasing up until this point. Let's say that is 17 minutes. Then from 17 minutes going up to that point, all the way up to that point, let's say that point is 26 minutes. So the temperature is constant here. Temperature is still constant, it's still 93 Celsius degrees. Then the temperature starts to increase again. It goes up again from this 26 Celsius degree, 26 minutes up to 30 minutes. So what I want you to observe now is that at the melting point, the temperature is constant, it's not changing. At the boiling point, the temperature is constant, not changing. It's not changing, it's constant. So the temperature only changes when it's going up here, when it's going up here, when it's going up there. So this question now is asking, what happens now to the temperature while the substance melts? So we are looking now at the melting point. Here is the melting point. The melting point, it is this phase, this temperature where the substance is 54 Celsius degrees. And it's remaining constant now from 5 minutes up to 12 minutes. So what happens to the temperature? We say there that the temperature remained constant. That's what happens. The temperature remains constant. Why it remained constant? because at that state, that means that the energy was used now to break the bonds. You remember we had in the solid state the bonds of water, the water molecules or particles, they were closely packed to each other. This was a solid state. Now the solid state now is moving from solid to liquid. So what now happens when you increase the temperature? Remember, we increase the temperature and the temperature reach the melting point. So when you increase the temperature, you are also increasing the average kinetic energy. So that means that at that point, which is the melting point, all this energy now was used to break these bonds. You have to break these bonds now. We have to break these bonds, you have to break these bonds, you have to break these bonds to get the molecules separated from each other so that it can move. It's no longer liquid now, it's no longer solid, now it's liquid. That means at that point now, at the melting point, all the energy was used. The energy was used to break the bonds during the phase change. Because of now the phase is changing, so now all the energy was used to break the bonds here at this point. And also, so if all the energy was used now to break the bonds, that means now there is no available energy to increase the average kinetic energy of the particles. Now remember that melting point remained for how long? From 5 minutes up to 12 minutes. That means all this time, the particles are just stationary. The particles are just moving at that rate. So it's like it's a liquid state. The temperature, if the temperature is constant, that means there is no available average kinetic energy. So it's going to remain like this up until after 12 minutes. We see the temperature increasing. So when the temperature increases now, that means the average kinetic energy is also increasing. Then they begin to move at a faster rate now because they have gained energy and they are colliding with each other up until they boil at 100 Celsius degrees. So that's why we said now at the melting point, all the energy was used to break the bonds during the phase change. And there is no available energy now to increase the average kinetic energy. That's why it's in the state like it's like it is at a constant state for all that 5 minutes to 12 minutes. So to get that 3 marks, you must have 3 points. That at that point, at the melting point, the temperature remains constant. If the temperature is constant, that means that the energy is all used to break the bonds and there is no available energy to increase the average energy. That's why it is constant. That is the end of the question 3.4. So now I'm going to do the second question, which is similar to this one. Then we are done with this concept of the kinetic molecular theory. So let's go now to the next question. Okay, so this is the next question now. It's also question 3 of the kinetic molecular theory. It's a paper 2 question. So the question says here now, the table below shows the boiling and melting point of substances A to D. So now we have 4 substances. We have substance A, substance B, substance C, substance D. These are the boiling points in column 2 and we have melting points in column 3. So the first question now, question 3.1.1 says define the term boiling point. Define the term boiling point. So if we remember, the boiling point was this point. The boiling point was this point. It was, for water for example, it was 100 Celsius degrees. So what do we say happens at this point? The boiling point is the temperature when the liquid was changing into gas state. So what is the boiling point now by definition? So we are going to check on the exam guidelines for grade 10s. So the exam guideline says that when we define the boiling point, we need to say the boiling point is the temperature of a liquid at which its vapor pressure equals the external atmospheric pressure. So it's a temperature of a liquid with its vapor pressure equals external atmospheric pressure. So it's like vapor pressure is equals to ATP. So the vapor pressure of a liquid, temperature of a liquid at which its vapor pressure is equals to atmospheric pressure. Yeah, so that is a definition that they are looking for. So that's a boiling point. Then from the above table, write down letters A to D that represents the substance which is a liquid at 100 Celsius degrees, solid at 100 Celsius degrees, gas at 25 Celsius degrees. So we're going to use the table now. Then we're going to state now which substance represent liquid at 100 Celsius degrees, solid at 100 Celsius degrees, gas at 25 Celsius degrees. So in order for us to be able to answer this question, let me just show you a simpler way. Okay, if you look at the table for substance A, the melting point of substance A is negative 117 Celsius degrees, and the boiling point is 78 Celsius degrees. So we are looking now for at 100 Celsius degrees, what is the state of substance A? So let's look at this one. Now this is substance A. Substance A, the melting point of substance A is negative 117 Celsius degrees, and the boiling point of substance A is 78 Celsius degrees. Remember, we are moving from solid to liquid to gas. So this solid is going to melt now at this temperature, negative 117. When it is liquid now, substance A will boil at 78 Celsius degrees to become gas. So where is 100 Celsius degrees in this temperature? So if you do a number line here, so 0 must be somewhere here. Let's say that is 0. Where is 100? 100 must be somewhere here, above 78. So at 100 Celsius degrees, substance A, we see that it is a gas. So it is not liquid. Remember, the question was saying a substance that is a liquid at 100. So we are looking for a substance that is a liquid at 100. So we saw that the substance A at 100 Celsius degrees, it is a gas, it is not a liquid. So we cannot take substance A. Let's look at substance B. Now, substance B, melting point is 133, boiling point is 444. So here is substance B. The melting point of substance B is 133 Celsius degrees. Boiling point is 444 Celsius degrees. Now where is 100 Celsius degrees here? Remember, it is moving this way. So where is 100 Celsius degrees? Surely 100 must be somewhere here. So we can see that substance B is a solid at 100 Celsius degrees. When it increased temperature to reach 133, it will be a liquid. You increase that temperature to 444, it will become a gas. So that means that substance B is not what we are looking for. It is not a liquid at 100 Celsius degrees. Now let's look at substance C. Now substance C, the melting point is negative 220. The boiling point is negative 188. So this is substance C, melting point negative 220 Celsius degrees, boiling point negative 188 Celsius degrees. Now if you look at this at the number line, where is 100 here? 0 might be somewhere there. 100 must be somewhere there. Remember, these are the negative values, so all of these are negative. So 100 Celsius degrees, the substance C is a gas because 100 is above negative 188. So the answer is not C, because at 100 Celsius degrees, substance C is a gas. Now let's look at substance D. Now substance D at melting point is 90 Celsius degrees and the boiling point is 184 Celsius degrees. So here is substance D. So the melting point is 90 Celsius degrees and the boiling point is 184. So maybe where is 100 here? Surely 100 must be somewhere here in the number line. So from, let's say 0 is here up to 90, it's a solid. From 90 to 184, it's a liquid. From 184 going further, it's a gas. So 100 is here. That means that substance D is a liquid at 100 Celsius degrees. So the answer to this question, from above table, write down the letter that represents substance which is a liquid at 100. That is D. D is a liquid at 100. Which one is a solid at 100 Celsius degrees? Okay, let's look at the table again. So I rearranged now the table. I put all of the substances with the melting points and the boiling points. So let's look at 100 here. At A, we said 100 is here. So A is gas at 100. Let's look at B. Where is 100 here? 100 must be below 133. So 100 must be here. So B is a solid at 100. Let's look at C. Where is 100? 100 must be up here. So C is a gas at 100. Let's look at D. We said where is 100 here? 100 must be between 90 to 184. 100 must be somewhere here. So that question that was asking, which one is a liquid at 100, we said is D. Yes, D is a liquid. Here is it. It's a liquid at 100. The next question, which one is a solid at 100? So the one that is a solid at 100, can see it is B. Here is 100. It's a solid at 100. So the answer for this one, B, is a solid at 100. Now number C, which one is a gas at 25 Celsius degrees? So we want now to see 25 Celsius degrees. Where is 25? Okay, let me put here, look at A. Above 78, you cannot get 25. 25 must be this way. So remember, we are looking for the one that is a gas at 25. So it cannot be A. A is not a gas at 25. Look at B. You cannot get 25 above 444. 25 must be somewhere below here. So it's not B. Look at C. C, we can have 25 above negative 188. 25 can be somewhere here going further to 100. So that means substance C is a gas at 25. D, above 184 you cannot get 25. 25 must be somewhere here below 90. So the only answer is C. C is the gas at 25 Celsius degrees. Yeah, so we're done with this one. Let's look now at the 3.1.3. Which one of the following diagram represents particles arrangement of substance A at negative 120 Celsius degrees? Write down only 1, 2, or 3. So if you look now at this diagram, diagram 1 shows a solid. Diagram 2 shows a liquid state. Diagram 3 shows a gas state. So which one of the following diagram represents particle arrangement of substance A at negative 120 Celsius degrees? So negative 120 Celsius degrees for substance A. Where is negative 120? It must be above 78. So, it must be below negative 1. Remember, we are looking at the negative values now. So if let's say 0 is here, so this is a number line. So all of these values are negative, negative, negative 170, negative 180, negative 190, negative 120. So negative 120 for substance A would be a solid. And which diagram is a solid? It is diagram number 1. So that means that the answer for which of the following diagram represents particle rearrangement, we said is diagram 1, because they said write only, is it 1 or 1, 2 or 3? So we choose diagram 1 because substance A at negative 120 is a solid. So that's the end of that one. So now we are moving to 3.2. We have this heating curve. Heating curve of the substance is shown below. Look at the questions. Write down the physical state of the substance at 15 minutes. At 15 minutes, here is 15 minutes. What is the state? Look at 15. Okay, let's look at this first. So we know here is a solid phase. Here is a liquid state. Here is a gas state. And we know that this is our melting point. And this is our boiling point. So at 15 Celsius degrees, at 15 minutes, what is the state of a substance? The state of a substance is a liquid. As you can see, this is a 15 minutes. It's pointing here at a liquid state. So we say the answer is liquid. That's a liquid state. What is the boiling point of the substance? The boiling point of a substance. Now, here is a boiling point. We need now to see what is the value on the y-axis. What is the value on the y-axis? So we need to check now this value. So what is the difference in this graph? 0 to 40. So that means this graph goes by 40 plus 40, that's 80, plus 40, that's 120, plus 40, that's 160. So it goes by 40. How many blocks in between? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means 40 divided by 10, that is 4. That means each block now is 4. So how many blocks we are looking at now? Okay, let's say the boiling point is here. How many blocks is that? 1, 2, 3. That means from 120, we're gonna add 3 blocks. Each block has a value of 4. So we have 120 plus, we have 3 blocks. Each block is 4. So it's 120 plus 4, 8, 12. So 120 plus 12 is 132. So that's 132 Celsius degrees. So this point here is 132. So from 180 you add 4, 8, 12. So if you add 12 to 120, you're going to get 132. So the answer here, what is the boiling point? The boiling point is 132 Celsius degrees. How will the average kinetic energy of the particles of a substance be affected? Write down only, increase, decrease, remain the same at t 0 minutes and t 5 minutes. So at 0 minute to 5 minutes. So from here, from 0 to 5, how will the average kinetic energy be affected? Is it going to increase, decrease, remain the same? Remember, the average kinetic energy is the measure of the temperature. So that means that if we are saying that the temperature is increasing, look, the temperature is increasing from 0 to 5. So if the temperature is increasing from 0 to 5, that means the average kinetic energy is also increasing from 0 to 5. Because of we saw now the temperature from 0 to 5 is increasing. But from 5 to 10, the temperature is constant. The temperature is constant. That means here the average kinetic energy is also constant, or it remains the same. Then from there you can see now from this time going further up to that time the temperature is increasing. That means the average kinetic energy is also increasing. But you look now at the boiling point, from this time to that time the temperature is constant. That means the average kinetic energy is also constant. Then from this time to that time the temperature is increasing, the average kinetic energy is also increasing. So the question was saying, let us look at 0 to 5 and check what happened to the average kinetic energy. We said from 0 to 5, since the temperature is increasing, we know the average kinetic energy is also increasing. So we choose increasing. So the answer here is increasing, or increases. From 5 minutes to 10 minutes, from 5 minutes to 10 minutes, we see it is, the temperature is constant. That means the average kinetic energy is also constant. So we choose remain the same. That's what constant mean. We choose remains the same. In other words, it's not changing, it's constant. Last question now. Refer to the kinetic molecular theory. Fully explain the answer to question 3.2.3b. 3.2.3b is this one, where we said that the average kinetic energy is remaining the same. Let's use the collision theory, the kinetic molecular theory, and explain why we say it remains the same. So this one is similar to the previous question we answered. We said now when that average kinetic, the reason that average kinetic energy remains the same is because at that point, at the melting point, the temperature remains constant. Therefore, when the temperature remains constant, that means all the energy is used to break the bonds It's used to break the bonds between the molecules of that substance, and at that point now there is no enough energy to increase the average kinetic energy of the particles. Remember, the average kinetic energy has to do with the velocity or the motion. So that means that the reason that those particles at that state now they are just constant is because of now the average kinetic energy is also constant. Why? Because the temperature is constant. If the temperature is constant, the average kinetic energy will be constant. That means the velocity of the molecules will also be constant. So that's why they are just vibrating, or they are just moving at a slow pace. This is the liquid state, because the melting point now has changed them from solid to liquid. So that's what is happening. That's why now they remain the same. The temperature remains the same. That means the kinetic energy will also be constant, and the average movement, the speed of the molecules will also be constant. That's what is happening at that state. So that was the last question now in our video. So we are done with 2 questions on the kinetic molecular theory. I think by now you have an idea of what is going on. Before now we finish the video, let me quickly explain. We mainly explain the liquid. Now what happens when the gas moves now from liquid, when the substance moves from liquid to gas? What happens to the average kinetic energy? So remember, we're going to heat now the liquid. Let's say, for example, at 100 Celsius degrees, it starts to boil. That's a boiling point. Then the substance is going to have now gas state. These are the molecules of a gas state. What is happening here is that when you increase the temperature, in the liquid state, you are also increasing the average kinetic energy, which means they are also increasing the speed of the molecules. So you are increasing the speed of the molecules. The molecules now are moving at a higher speed. That's when at the liquid state they collided with each other, collided with the walls of the container, and they change now from liquid to gas molecule. So that means that at the gas state, the average kinetic energy is very high, and the velocity of the molecules is also very high. The bonds now have been broken completely because of we increase the temperature. Then by increasing temperature, you're increasing the average kinetic energy, you're also increasing the velocity of the molecules. So that's what is happening at the gas state. In case maybe they ask that question in the future. Yeah, that's the end of our question. I will see you now in the next video when we are doing the periodic table.